Welcome to Tech Teach.
In terms of design perspective, we will be looking at like how we should be proceeding with the design. So we will just take it from here. So that will be like the design of counters. So in design of counters, we will be looking at how we can design the synchronous counters and asynchronous counters. So one by one we will be looking. So we will be starting with like how we can design the synchronous counters. So first we will be looking like design of synchronous counters. So in case of synchronous counters, we already know like in synchronous counters, all the flip-flops will be connected with the same clock. So all the flip-flops will be having the same clock into the synchronous counter case. And also how many flip-flops will be used, that will be depending on the number of states. And also in synchronous counters, the counting can be in any order. So first thing we will be writing like counting can be in any order. So there is no need to have a fixed counting sequence. It will not be an ordered one. It will be having a random sequence of the counting. For example, it may be asked to count like 0, then 5, 2, 3, 4, 1, then 0. It may be likewise also. So like this is a random sequence. So if it is a synchronous type of counters, then only this random type of or any order type of counting is possible in synchronous. In asynchronous, there is a fixed counting pattern. Either it will be up counter or down counter. So I hope it is clear by now. So once we are going to design the synchronous counters, we can take any random count. And also for designing the synchronous counters, we can use the flip-flops that can be either D flip-flop, or it can be T flip-flop, or it can be JK flip-flop. But it is not so in case of asynchronous. So while designing the asynchronous type of counters, we should be only taking the flip-flop that is having the toggling case, that is J and K, JK and T flip-flop. So that we will be taking it in the coming slides. Okay. So this is the condition, like counting can be in any order. The flip-flop that we can use is any flip-flop we can use, and clock is common for all flip-flops. The clock is common for all flip-flops in case of the synchronous counters. So we will be proceeding with an example. So suppose we are going with an example, and in that, suppose we are using the D flip-flop for designing the sequence. So suppose a sequence is given. So suppose this is the sequence that is given, the same sequence. So design, the question will be like design a synchronous. So here it is like how many states are there, you can just look at it. So how many states? So 0, 1, 2, 3, 4, 5. So total in the sense 6 states are there. 1, 2, 3, 4, 5, 6. And this is again the repetition is there. That meaning after that the pattern is repeating. So unique states are 1, 2, 3, 4, 5, 6. 6 states are there. So design a synchronous counter with following sequence. The sequence is 0, 5, 2, 3, 4, 1. Yeah, so this is the sequence you need to design. So we will be looking like how we can start. So there are different steps that we need to follow while designing the counters by using the synchronous mode. So synchronous mode counters we can design by using few steps. So what are that steps? So first step that we basically follow is we need to identify identify the number of states. So how many states are given into the question we need to identify. Once you have identified the number of states, now we need to identify the identify the number of identify the number of flip-flops required. We need to identify how many number of flip-flops will be required. So after the identifying the number of flip-flops that is required, we need to design, or we need to construct the state table. We need to construct the state table. So we will be looking like how the state table is implemented. So we have already seen in the previous classes also, but we'll be going to see like how the state tables are basically constructed. And then the fourth step will be like write down the excitation equation, or with the help of excitation table, write down the excitation equation, or we can be calling like write down the excitation table. So excitation table for different flip-flops we have already gone through. The same excitation table we will be using. So either we are using D flip-flop, T flip-flop, or JK flip-flop. We can use the excitation table of that particular flip-flop. So in the question, it may be given like implement by using D flip-flop or okay. So in the question also design synchronous counter with following sequence using D flip-flop. It may be given, or it may be given like T flip-flop, or it may be given like JK flip-flop. So you can implement by using any of the flip-flop. We will just see the procedure will be the same. Okay. So write down the excitation table for the used flip-flop. So here, so whatever flip-flop, suppose we are going to use D flip-flop. So whatever is the excitation table of the D flip-flop, we need to write after establishing the state table. So whatever state table is there, in that we will be writing the excitation table of the D flip-flop now, if we are proceeding with the D flip-flop. So for here, D flip-flop as it given in the example. So once we have written down the excitation table, next, based on the excitation table, we need to find out the inputs of the flip-flop. So to find out the inputs of the flip-flops by using the same state table and excitation table, we will be able to find out what will be the inputs to the flip-flop. Okay, so in that, so we need to write down what will be the Boolean expression for these inputs. So now we need to write down or obtain the Boolean expression for the inputs of the flip-flops. We need to find out the Boolean expression for the inputs of the flip-flop and minimize it. or we can just write it down like obtain the minimized Boolean expression. We can write it down, obtain the minimized Boolean expression. Obtain the minimized Boolean expression for the inputs of the flip-flop. The last step is implement the circuit diagram using flip-flops and logic gates. So finally, we need to implement the circuit diagram by using the flip-flops and the logic gates. So these are the steps. So we will be proceeding one by one. So first of all, here we are going to use the D flip-flop. So once we are going to use D flip-flop, we have decided we will be using D flip-flop. Then the first step is identify the number of states. So here, how many states are there? Total 6 states are there. How many states? 6 states are there. So 6 states are like they're having the value n. Similarly, we need to find out like how many flip-flops are required. So flip-flops required is basically given by small n, that is log n to the base 2. So n should be greater than or equals to log n to the base 2. So if we put the value of 6, so your n value will be coming out to be 3. It should be an integer. So n value is 3. Its meaning is 3 flip-flops will be required. So it is here 3 flip-flops will be required. So how many flip-flops are there? That meaning 3-bit counter it will be there. So it will be a 3-bit counter. Its meaning 3-bit will be used to represent one state. So 3-bit will be used to represent one state. So what is the states basically? So it is 0, 5. So its meaning is 0, 5, 2, 3, 4, 1. It is after 1. So after 0, it should be 1. After 0, it should be 5. After 5, it should be 2. After 2, it will be 3. After 3, it will be 4. 4, then 1. After 1, it will be 0. And then it will be repeating likewise. So now, and we have got it 3. It's meaning 3-bit will be required to represent one state. Each state will be represented in 3 bits. So we need to construct the state table now. So state table. So in the state table, what terms are there into the state table? So in the state table, what inputs are there here is, so one is basically called like present state. So there will be a present state. So present state, because 3 flip-flops are there. So if it is present state, so 3 flip-flops in the sense Q and 0, we can write it down, or we can represent Q0, Q1, and Q2. So 3 flip-flops will be used. So this is the present state of the flip-flops. Then after present state, we will be having the next state. Next state of the flip-flop. So in the next state, we have generally write like Qn plus 1. So instead of writing Qn plus 1, we will be writing like Q0. Here we will be making it plus. So it indicates like we are talking about the next state. So Q0, Q1 plus, Q2 plus. So there is a present state and there is a next state. And with respect to the present state and the next state, there will be the output. And that output we will be basically considering here is like the excitation table of the D flip-flop that we are using here. So what is the present state and next state? We will just writing it out. So present state, so initially it was 0, 0, 0. Yeah, before constructing this state table, we will be constructing here the state diagram also. So how we can write it down is here state diagram and state table. State diagram and state table as well. So what is the state diagram? So states are like 0, then 5. So 5 is 1 0 1. After 5, the state is next state is 2. So next state is 2. So 0 1 0 is the 2. After 2, it is 3 and 4 1. Just 3, then 4, and then 1. So these are the state diagram. This is the state diagram. So from 0 it is going to 5, then after that 5 it is going to 2, after 2 it is going to 3, then after 3 it is going to 4, and then 1, and then 0. This is called the state diagram that we have already seen how to construct state diagram. So once we know the states, based on that, whatever the sequence, we will be putting it into the sequence. So this is the state diagram. So with the help of a state diagram, you can just see this is the present state. So what will be the next state? So if it is at 0 0 0, the next state will be 1 0 1. The next state is 1 0 1. Similarly, if it is at, okay, one more thing. So either we can take, because we will be considering all possible, because this is considered like the 3 inputs. Okay, so all possible combinations we will be considering. So it is 0 0 0 0 0 1. Okay, 0 0 1 0 0 1 0 1 0 0 1 1 1 0 0 1 0 0, then 1 0 1. Okay, likewise. So here you can just see after 0 it is going to 5. After 0 the next state is 5. After 1 the next state is 0. So after 1 the next state will be 0. After 2, so this is 2. After 2 next state is 3. So you're writing like 0 1 1. After 3 the next state is 4. So it is 1 0 0. After 4 the next state is, after 4 next state is 1 0 0 1. After 5 the next state is 2. That is 0 1 0. So I hope you are getting this. Either we can write likewise, or we can have like this order also. Like we can also write the first is 0, it is going to 5. Then here we can write 5, and after 5 it is going to 2. After 2 it is going to 3. After 3 it is going to 4. After 4 it is going to 1. After 1 it is going to 0. Likewise also we can write, or we can write like in this manner also. Or what we can do is just write it down with respect to that only. So both the steps are okay. You can proceed with any one, because in final one we need to simplify with the Boolean expression to get the expressions, okay, of the input. So that will not be having that much no difference. It will be, so the difference we can write down the different states also. So it is 0, it is going to 5. Then from 5 it is going to 2. Then from 2 it is going to 3. Then from 3 it is going to 4. So from 4 it is going to 1. Then from 1 it is going to 0 0 0. So this is the relation between present state and next state from the state table, state diagram. We can get it. After that, now we are going to design this counter with the help of D flip-flop. So if we are going to use the D flip-flop, and there will be 3 different D flip-flops. So D0, D1, and D2. 3 different flip-flops will be there, D flip-flops. These are basically called inputs of flip-flop. So we just want to relate like how the inputs of the flip-flop will be related with the next state and present state. So, or we can say like we are going to constitute like how the flip-flops will be excited based on the present state and the next state, or the present state and the next state in the sense. So the relation between the present state, next state, and the inputs of the flip-flop is given by the excitation table. So now in the next step, it is given like after the state diagram and state table, we need to write down the excitation table for the used flip-flop. So we are using D flip-flop here. So if we are using D flip-flop, we will be using the excitation table of the D flip-flop. So here the D0, D1, D2 values will be taken from the excitation table. In the excitation table, the relation is in the excitation table is having basically. So excitation table is having the values like Qn, then Qn plus 1, and then the input of is flip flop input. So for D flip flop, this was the table. So this we have already seen. Okay. So in that, what was that? Is like these two will be the inputs, and this will be the output here. So here 0 0 0 1 1 0 1 1. So that we have already seen, but I am just recalling it. So if this is the case, so if previous state is 0 and the next state is 0, at that time D should be 0. If D is 0, then only this will be the possible. Similarly, if present state is 0, present state or previous state that we are I'm saying, so that is similar. It's like whatever is the present state and the next state. Next state is after the new clock that is coming. So after the clock, whatever will be the output. And before the clock, the output is either present state, we can call it, or the previous state. Okay. So present state is 0 and next state is 1. It's meaning T should be 1. Then only it is possible. So you can just look at it, how the excitation table is there. You can just go through the previous videos I have already shared. You can just go through it. So in this case here also, if Qn, that's present state is 1 and the next state is 0, it's meaning T should be 0. If here again previous state is 1, next state is 1, it's meaning T should be 1. So this is the excitation table of the D flip flop. This is the excitation table of D flip flop. So from there, this excitation table, we can fill the value here. So once we are going to fill the value here, you can just look at it. So D2. So this D2 will be depending on the Q2 and Q2 plus. So Q2 and Q2 plus will be deciding the D2 value. So previous state or present state is 0 and next state is 1. So D value should be 1. If the previous value or the present value is 1, the next value is 0, it will be 0. It's meaning the D is decided based on the next value, next state value. So next state is this value, same value will be here. So we can just copy and paste. Okay. Similarly for D1, this value will be there here. So it will be 0. This is 1. This is 1. This is 0. This is 0. And this is 0. Similarly, this is there. So it is 1. This is 0. This is 1. This is 0. This is 1. And this is 0. So I hope you have got this, like how we have. So this table that we have just inputted, that is with the help of excitation table. With the help of excitation table of the D flip flop. So from the excitation table of D flip flop, we can be filling these values. So once we have filled those values, now we will be getting to know like how this D is expressed. So for each of the inputs of the flip flop, this D0, D1, D2 is the input of the 3 different D flip flops that will be used. So what will be the expression for this D0, D1, D2? We will be simplifying by using the K map again. So we can just think of it here. D2. D2 is here, 1 here. It is 1 here. These are the two terms that is explaining the D2. Similarly, with the help of K map, we will be simplifying it. So for D2, the K map will be like, so how the K map will be there? Because here Q0, Q1, Q2, 3 inputs are there. So these 3 inputs will be part of the mean terms. Okay. So once we simplify it, we can simplify 0, 1, 2, 3, 4, 5, 6, 7. So this is coming out to be like 1 is here at 0 and at 3. At 0 and add 3. So here with respect to that, they cannot be combined together. They cannot be combined together in the sense, then D2 value will be given like, this is basically like, this is Q2, this is Q2 bar, Q2, and Q1 and Q0 bar like this. So this is Q2 bar, Q1 bar, Q0 bar plus Q2 bar. This is Q1. This is the D2. Similarly, we need to find out for D1. So for D1, this is the mean terms. So this is mean term is, this is 5 and this is 2. So 5 and 2. So 5 and 2, again it is not related. So for D1, the expression will be directly we can get from here. So this is Q1, Q2, Q1 bar, Q0. Okay. So this is Q2, Q1, Q2, Q1 bar and Q0 plus this is Q2 bar, Q1, Q0 bar. So this is the D1. Similarly, D0 we will be finding it out. So for D0, we can get like this term, and this term. So this is 0, this is 2, and this is 4. 0, 2, 4. So if you put the values 0, 2, and 4, so 0 and 2, for this we can just simplify it. So this is for D0, for D0, 0, 4, and 2. So we can have a pairing here. We can pair it likewise, or we can pair it this way also. So the expression for D0 will be, so the expression for D0 will be like, this is Q1 bar, Q0 bar plus Q2 bar, and here it will be like Q1, Q0 bar. Okay. So Q0 bar is common here. So this will be the expression for D0. So after simplification, the expression for D0, D1, and D2 we have got. So once we have got the expression for this, we have got the expression, that is minimized expression we have got, and then we will be implementing the circuit diagram by using the flip-flops and the logic gates. So how the circuit diagram will be looking like? So first of all, there will be 3 flip-flops. So there will be 3 flip-flops. This is D2, Q2, Q2 bar. There will be the clock. D1, Q1, Q1 bar. There will be a clock. D0, Q0, Q0 bar. There will be a clock. The clock will be connected. Same clock will be connected with all the flip-flops. This is the clock. Okay. Next comes the inputs that we will be applying. So how the inputs will be applied is, you can just look at it here. D0. How the D0 will be looking like, or how the D1 is there and how the D2 is there. So D2 will be related with, so D2 will be having 2 AND gate. So this is one AND gate, this is another AND gate, and one OR gate. So expression for D2 will be the combination of D0, D1, D2, and it's and then operation OR. So we will be ORing it out. So we can just, so there will be OR of the 2 AND gates, and the input of the AND gate, one AND gate and another AND gate. Three inputs will be there, and here 3 inputs will be there. So what will be the 3 inputs? That is Q0 bar, Q1 bar, and then Q2 bar. So either we can connect these one because Q2 bar is here, we can connect here. Q1 bar we can connect here. Q0 bar we can connect here. Or because of the complexity, we will just writing it down. So Q1, Q0 bar, Q1 bar, and Q2 bar. And then this one will be like Q0, Q1, sorry, Q0, Q1, Q0, Q1, and then Q2 bar. So this is the expression for D2. So this is the D2. Similarly for D1. So what is the expression for D1? So D1 is here. This is the expression again here. It will be requiring like OR gate and then two AND gates will be required. 3 inputs will be here also. And 3 inputs will be here also. So what is Q0, Q1 bar, Q2? So Q0, Q1 bar, Q2. Next one is Q0 bar, Q0 bar, Q1, Q2 bar. This is the expression for D1. Similarly, the expression for the D0. So D0 will be this one. So D0 will be like there is another OR gate is required. Okay. So this is the OR gate, and the two inputs will be like with one AND and then another AND gate. So this will be Q0 bar, Q1 bar, Q0 bar, Q1 bar, and then Q0 bar and Q2 bar. Or we can further simplify it like we can take the Q0 bar common and it will become like Q1 bar plus Q2 bar. So for this, so in this case, we'll be requiring one more, one less. This is Q0 bar, and this will be the OR gate. So for bar, we need not to use the NOT gate because the Q0 bar is available with us. Q2 bar is also available. We can directly connect. So only the connection problem is there. So that's why I haven't connected. So it becomes too complex. So it will not be able to clearly visible like which line is going from where. So that's why I have just the values here. So Q0 bar, Q1 and Q2 are likewise. So this is how it will be connected. So now this is the case where these are the four outputs Q0, Q1, and Q2. So finally, if you analyze this circuit, once you will be analyzing it, if you will be getting to know the timing diagram. So timing diagram in the sense, so what will the clock in Q2, Q1, and Q0. So once you will be getting to know for each of the clock, you will be getting to know like if initially it is 000, the sequence it will be counting is the one that we have just implemented. So once you will be putting the value, you can get to know like for each clock, for the first clock, then second clock. So if all are zeros, the next clock is there. So for that, what will be the output? You can just calculate from here. So after that, so suppose if this is 0, so you can look at it. If this is 0, this will be 1. If this is 0, this is 1. If this is 0, this is 1. So from here you can just see Q1 and Q2 bar. Q1 and Q2 bar is 1 1 or will be 1. Then this is 1 and with Q naught 1. See, this is 1. So this one is 1 means D naught is 1. So in the next clock, it becomes 1. Similarly, for the second one, we are just verifying whether we have got the correct one or not. So if it is 5 is coming, then its meaning is we have just verified it. Again, yeah, if it is 0, 0, 0, all of the 0, 0, 0, this will be 1, this will be 1 again, this is 0, 0, 0, and this is 1. Okay, so for this output, Q, yeah, so any of it is 0, so it becomes 0. Here also, if anyone, if it is 0, so all are 0, so it will be 0. So overall, this is 0. So overall, the Q1 will become 0. Similarly, in this here, you can just look at it. So here in the first one, all are having bar. All are having bar in the sense one and with one and with and. So this will be having 1 and this will be 0. So out of this, the value will be 1. So overall, if we are putting the value 1 to the flip flop, output will be 1. So you can just look at it. The same after 0, 0, 5 is coming. In the next clock, you will be coming. So the next steps will be coming. You can just verify it. Okay. The same thing is there. So you will be getting the next sequence, that is 0, 1, 0. You will be getting the 0, 1, 0. 0, 1, 0. Likewise, you will be getting all other uh, sequences. In the third clock, after 0, 5, 2, it will be getting 3, and then it will be getting 4, then it will be getting 1. And after that, it will be repeating again with 0 and then proceeding like that. So this is how we basically proceed while implementing synchronous type of counters.